Hello, everyone. My name is Sami Lama. I'm a mechanical engineering major, and today I'll be talking about the heavy lift drone, which was made in conjunction with six other team members from the mechanical engineering department, the aerospace department, the electrical engineering department, the computer engineering department, and the computer science department. So, our initial goal with the heavy lift drone was to create a multi-purpose unmanned aerial vehicle that could have a total takeoff weight of 55 pounds and that could sustain flight for 20 to 30 minutes. Now, the reason that we want an upper limit of 55 pounds for takeoff is the Federal Aviation Administration requires advanced piloting licenses, namely the light aircraft license for anything above 55 pounds. So we thought we would simplify the process and have it be under 55 pounds. Now, to achieve that, we need to maximize the payload of the drone while minimizing the weight of the drone itself. So in the testing and analysis section, you can see some of the material selection analysis that we did, especially in the top left diagram, in order to determine what materials would be best suited for the drone. We not only looked at what materials were the lightest and strongest, we also looked at what materials we could realistically manufacture and other factors like that. We also did some tensile and bending tests for the materials of the heavy lift drone. You can see an example of the tensile test in the top right of the testing and analysis section. And we determined that the best two materials to use would be aluminum and PETG at 20% infill, which is a 3D printed plastic. But before I go more into testing analysis, on the bottom left in the concept of operations, you can see how the drone itself works. Since it's a multi-purpose drone, we decided to focus on one aspect of the drone, which we thought would be very useful, which is thermal imaging of agricultural fields in order to determine what areas of those fields need to be watered and what areas just need fertilizer. And this is done by looking at the relative temperature between different areas of the soil in a field. So for the concept of operations, once the drone is assembled and the control station is put up, the drone will take off, fly over the field for scanning in a mow the lawn approach, meaning it will try to take as few pictures as possible while maintaining the largest overlap, while maintaining the smallest overlap between these pictures. After it does that, it will land and disarm and then disassemble for storage. And at this point, a lot of the data will be sent over to a computer to process. Now, further on in the testing and analysis, once we determined what materials we wanted for the drone and such, we performed modeling and analysis of the drone, namely some drop tests, stress tests, and other analysis. You can see in the drone in the center image, there are also these ducts that go around the 12 propellers we have for the drone. And the reason for these ducts is to increase the lift efficiency of the drone. Now, one of the reasons we have the bottom right testing and analysis image is that we want to justify the use of these ducts, meaning the ducts add weight to the drone, but we need the lift efficiency as a result of these ducts to be higher than the added weight that they put on the drone. Now, as you can see, we also have a prototype quadcopter right in the center of the poster, and that we successfully achieved hover testing with that prototype. But unfortunately, we were not able to complete the larger final drone, although that's due to developments from COVID-19 restricting our access to some manufacturing facilities as well as delivering items to us. Although it is mostly complete, as you can see in the results and future work section, although some materials have been replaced with more easily accessible ones, such as the carbon fiber plate in the middle being replaced with plywood. However, in the future, we'd like to develop a custom undercarriage. Another good idea is to have collision avoidance. Now, the drone has autonomous flight, meaning it will stabilize itself in flight, but it does not have collision avoidance. It's also somewhat difficult to take apart and store, so optimizing portability would be a good idea. We are confident that whatever senior design team will pick this up next year has a great platform that we've developed to work on. Thank you so much for listening.